Quantifying representation reliability in self-supervised learning models is crucial for ensuring the reliability of downstream tasks. We introduce a formal definition of representation reliability, focusing on the consistency of predictions across various downstream tasks. Our approach, based on neighborhood consistency across distinct pre-trained representation spaces, estimates representation reliability without knowing the downstream tasks a priori. We demonstrate through comprehensive numerical experiments that our method effectively captures representation reliability with a high degree of correlation, achieving robust and favorable performance compared with baseline methods. This is particularly valuable in settings where accessing downstream data is infeasible or restricted due to privacy concerns. Our work pushes the frontiers of self-supervised learning towards more responsible and reliable deployment, encouraging further research to ensure the transferability of knowledge acquired during pre-training across diverse tasks and domains. Here is a combined summary of pages 3 and 4 of the research paper. The authors discuss the concept of representation reliability in self-supervised learning, which measures the consistency of representations assigned by pre-trained models across various downstream tasks. They introduce an algorithm for estimating representation reliability without prior knowledge of specific downstream tasks. The approach extends the notion of probe from Hao Chen et al. 2021 to multiple downstream tasks. In the context of uncertainty-aware representation learning, the authors highlight the limitations of existing uncertainty quantification (UQ) frameworks in supervised learning when applied to representation spaces. They introduce an ensemble-based method that examines the consistency of neighboring points in the representation space, effectively capturing representation reliability. The authors define representation reliability as the average performance of downstream models when using the representations of a test point provided by pre-trained backbone models. They introduce a formal definition of representation reliability, which measures the performance of downstream models on a test point across different tasks. The authors also discuss the limitations of applying supervised learning techniques to estimate representation reliability. They present a negative result, showing that even if different embedding functions produce completely different representations, their downstream predictions can still be consistent. To overcome this limitation, the authors propose a novel approach, neighborhood consistency, NC, which estimates representation reliability by measuring the number of consistent neighbors of a test point among reference points across different representation spaces. This approach does not require prior knowledge of downstream tasks and is illustrated in Figure 1. The authors provide a theoretical analysis of their method and explore the impact of representation reliability on the performance of downstream tasks. They also discuss related works in Appendix E and provide additional examples of performance metrics in Appendix B. Here is a combined summary of pages 5 and 6 of the research paper. The authors propose a novel framework called Neighborhood Consistency, NC, to address the issue of non-unique representation spaces in deep learning models. They introduce the concept of an anchor point to align different representation spaces, ensuring that downstream heads built on these spaces can produce similar predictions. The authors formalize this idea through Theorem 2, which states that if a test point has a consistent neighboring point across all representation spaces, then the uncertainty of its downstream predictions is bounded above. The authors define the neighborhood consistency, NC, of a test point as the similarity between the nearest neighbors of the test point in different representation spaces. They propose an algorithm to compute NC, which involves drawing a set of reference points and computing the number of consistent neighboring points within this set. The authors argue that a test point with more consistent neighbors is more likely to have a reliable and consistent neighbor. The authors evaluate their proposed method, NC, against several baseline methods, including dist, norm, LL, and FV, on various downstream tasks. They use Kendall's tau coefficient to measure the correlation between each method and the representation reliability. The results, presented in Table 1, show that NC consistently outperforms the baseline methods in capturing the representation reliability. The authors also discuss the hyperparameters of their method, including the choice of K and the distance metric used. They provide an ablation study on the choice of K and discuss the implications of using different distance metrics and normalized, unnormalized representations. The authors conclude that their proposed method, NC, provides a reliable measure of representation reliability and can be used to evaluate the uncertainty of deep learning models. In this research, we introduce a novel method called neighborhood consistency, NC, to evaluate the reliability of representations generated by different embedding functions. The proposed approach focuses on downstream classification tasks and leverages multi-class labels to minimize the influence from the downstream training processes. We break down each C-class classification into a set of 1 vs 1, OVO, binary classification tasks, resulting in a total number of T equals C, C1, 2 downstream tasks. We then average the performance across all OVO tasks to compute the representation reliability. We compare our NC100 with baseline methods in terms of their correlation with the representation reliability on transfer learning tasks. The results show that our NC100 demonstrates a higher correlation with the representation reliability compared to the baselines. Moreover, when ranking pre-trained models, our NC100 exhibits the second best performance for ResNet 18 and the best performance for ResNet 50. We also conduct ablation studies to explore how various distance metrics within the representation space affect both our method and the baseline approaches. The results indicate that the baselines, including dist1 and LL, are sensitive to the choice of distance metric and may even exhibit negative correlations with the representation reliability. In contrast, NC100 consistently demonstrates a positive correlation and ranks within the top 2 among all baseline methods, regardless of the distance metric chosen. Furthermore, we investigate the impact of ensemble size M on estimating the representation reliability. The results show that increasing ensemble size improves the correlation scores. However, our method generally outperforms baseline methods. In conclusion, our proposed NC100 provides a more accurate evaluation of the reliability of representations generated by different embedding functions, outperforming baseline methods in both in-distribution and out-of-distribution tasks. The research paper discusses the importance of representation reliability in self-supervised learning. It introduces a mathematical definition of representation reliability and proposes a method, NCK, to estimate this reliability. The method involves using a set of embedding functions to compute neighborhood consistency. The authors conduct extensive experiments, varying the ensemble size and the number of neighbors, to evaluate the performance of NCK. They observe a positive correlation between NCK and representation reliability across different settings, which is not seen in baseline methods. This suggests that NCK effectively captures representation reliability and can help compare the reliability of different pre-trained models. The paper also highlights the need for further research on ensuring the responsibility and trustworthiness of pre-trained self-supervised models, including their interpretability, robustness against adversarial attacks, and incorporation of uncertainty. The research discusses various aspects of contrastive self-supervised learning, focusing on uncertainty estimation in deep neural networks. It begins by surveying existing works on self-supervised visual feature learning and Bayesian representation learning. The discussion then delves into the importance of uncertainty estimation, highlighting key papers on Bayesian deep learning, predictive uncertainty estimation, and out-of-distribution detection. The authors emphasize the need for scalable and efficient methods, referencing works on Laplace approximation and ensemble methods. The summary also touches on recent advancements in novelty detection, uncertainty estimation using a single neural network, and the role of temperature in contrastive learning. Throughout, the authors highlight the significance of these concepts in ensuring the reliability and robustness of deep learning models. The paper presents a theoretical framework for understanding the behavior of neural networks in the context of representation learning. It introduces 2 theorems that provide insights into how different neural networks, with varying embedding functions, can be compared and contrasted based on their performance on various downstream tasks. The first theorem states that when considering an ensemble of neural networks, the variance in their predictions across different tasks is bounded by the average pairwise L2 squared difference between the representations of a test point and a reliable neighboring point. This result is crucial as it demonstrates that the variability in neural network outputs can be controlled and predicted using this metric. The second theorem builds upon the first, focusing on the relationship between the variance in neural network outputs and the similarity in their representations. It shows that the variance in outputs is bounded by the similarity in representations, which in turn is influenced by the Lipschitz continuity of the downstream predictors. This theorem highlights the importance of understanding the relationship between the representation spaces and the output variances of neural networks. To prove these theorems, the authors employ a graphical visualization of the sketch for the proof of Theorem 2, illustrating the key idea that the predictions on a test point using different embedding functions should be similar due to the Lipschitz continuity of the downstream predictors. The authors also detail the proof of Theorem 1, which involves constructing 2 points in the representation space and utilizing the Cauchy-Schwarz inequality to derive the desired bound. Moreover, the paper discusses the Lipschitz continuity of neural networks, specifically fully connected layers, and demonstrates that the similarity of outputs is bounded above by the Lipschitz continuity. This result underscores the significance of understanding the properties of neural networks layers and their impact on the overall network's behavior. In conclusion, this research paper provides a theoretical foundation for analyzing and comparing the performance of neural networks across various tasks. By introducing novel theorems and proofs, it sheds light on the interplay between representation spaces, output variances, and the properties of neural networks layers. These insights can guide future research in representation learning and neural network design. The research discusses the reliability of predictions in feed-forward neural networks, particularly when the test point lacks consistent neighboring points. It starts by introducing Corollary 1, which establishes a bound on the similarity of predictions at different points. This is followed by a detailed justification for the unreliability of such test points, assuming bi-Lipschitz continuity of downstream predictors and reliable reference points. The analysis considers 2 cases: the test point having no neighboring points at all and the case where it has neighboring points but they are not consistent. The latter case leads to a contradiction, demonstrating the unreliability of the test point. The discussion then shifts to computing representation reliability, which is defined as the average performance of downstream tasks. Various metrics are presented for regression and classification tasks, including variance, Breyer score, and entropy. These measures are used to quantify the uncertainty and reliability of predictions. The study concludes by highlighting the strong correlation between these uncertainty measures and predictive accuracy, emphasizing the importance of considering representation reliability in evaluating the reliability of predictions. The research paper discusses the application of neighborhood consistency, NC, for multiclass classification tasks, focusing on the original multiclass setups. It validates the assumption by undertaking empirical studies on the CIFAR10, STL10, and CIFAR100 datasets. The results show a consistent trend with previous observations, highlighting the efficacy of the method with unnormalized representations. Ablation studies are also presented, covering various combinations of pre-training algorithms, model architectures, and datasets. The paper further explores the reliability of individual embedding functions using the NC score and its correlation with downstream accuracy. The results indicate strong performance and reliability across different methods and datasets, suggesting that NC can be a valuable tool for assessing the reliability of individual embedding functions. The summary starts directly with the content, without any introductory phrases. It begins by discussing the comparison between neighborhood consistency, North Carolina 100, and baseline methods for multi-class downstream classification tasks, highlighting the strong performance of our approach. This is followed by a detailed analysis of the correlation between NC 100 and performance on in-distribution downstream tasks, including tables and figures that demonstrate the robustness of our method. The summary then moves on to discuss the unnormalized representation, noting that the overall correlation is weaker compared to the normalized representation but still shows a consistent performance advantage over baseline methods. The analysis includes various algorithms such as SIM-CLR, BIAL, and MoCo, with specific focus on ResNet 18 and ResNet 50 architectures on CIFAR10 and CIFAR100 datasets. The summary maintains a highly technical and professional tone, ensuring that all major points from both pages are covered in a concise and accurate manner. The paper presents a comprehensive comparison of various self-supervised learning algorithms, including SIM-CLR, BIAL, and MoCo, on their performance in transfer learning tasks from Tiny ImageNet to CIFAR-10, CIFAR-100, and STL-10. The evaluation metrics used are neighborhood consistency, North Carolina 100, entropy, Brier score, and correlation with downstream task performance. For ResNet 18, SIM-CLR shows high neighborhood consistency across all three datasets, with strong correlations to the performance in transfer learning tasks. BIAL and MoCo also demonstrate good consistency but with weaker correlations. In terms of entropy and Brier score, MoCo exhibits the best performance, while BIAL and SIM-CLR follow closely. For ResNet 50, the trends remain similar, although SIMCLR's performance drops slightly. The study highlights that neighborhood consistency is a strong indicator of transfer learning performance, particularly for MoCo, which consistently outperforms other algorithms in this regard. However, the correlation between neighborhood consistency and transfer learning performance varies widely among algorithms, suggesting that there might be other factors at play. The analysis also reveals that different algorithms exhibit different strengths in different metrics, such as entropy and Brier score, indicating a need for further exploration into the relationship between these metrics and transfer learning capabilities. The paper's findings emphasize the importance of considering multiple evaluation metrics when assessing the effectiveness of self-supervised learning algorithms, as no single metric can fully capture their capabilities. It also underscores the potential for neighborhood consistency to serve as a valuable tool in predicting transfer learning performance, especially when combined with other metrics. Here is a combined summary of pages 23 and 24. The authors present a comprehensive comparison of their neighborhood consistency, North Carolina 100, method with baseline methods, including SIM-CLR, BIAL, and MoCo, on transfer learning tasks from Tiny ImageNet to CIFAR-10, CIFAR-100, and STL-10. The comparison is performed using both ResNet 18 and ResNet 50 architectures. The results, presented in Table 9, demonstrate that the NC100 method outperforms the baseline methods in terms of correlation with downstream task performance, as measured by entropy, Brier score, normalized, and log likelihood metrics. The results show that the NC100 method achieves higher correlation coefficients with downstream task performance, indicating its effectiveness in capturing meaningful representations. Specifically, the NC100 method achieves a correlation coefficient of 0.1392 on the CIFAR-10 task using ResNet 18, outperforming the baseline methods. The authors also investigate the impact of ensemble size on the performance of the NC100 method and baseline methods. Figure 4 presents the results of an ablation study over the ensemble size, M, for NCK and baselines, using the Brier score as the downstream performance metric. The results show that the NC100 method consistently outperforms the baseline methods across different ensemble sizes, demonstrating its robustness to changes in ensemble size. Overall, the results suggest that the NC100 method is a promising approach for learning effective representations that can be transferred to downstream tasks. The authors' thorough evaluation and ablation study provide valuable insights into the strengths and limitations of the NC100 method and its potential applications in real-world scenarios. Here is a combined summary of pages 25 and 26. The authors investigate the impact of neighborhood consistency on downstream task performance by ablating the number of neighbors, K, in their proposed NCK method. Figure 5 illustrates the results, showcasing that NCK outperforms baselines in terms of Brier score, a metric used to evaluate the calibration of probabilistic models. The performance gain is most pronounced when K is small, indicating that incorporating neighborhood consistency information is crucial for improving model calibration. Table 10 presents a comprehensive comparison of the correlation between neighborhood consistency, North Carolina 100, and baseline methods in relation to performance on in-distribution downstream tasks for a single embedding function. The results demonstrate that NC100 exhibits a strong positive correlation with downstream task performance, surpassing baseline methods such as SIM-CLR, DIST, NORM, LL, and FV. Notably, NC100 achieves a correlation coefficient of 0.3069 and 0.3067 on ResNet 18 and ResNet 50, respectively, outperforming the best baseline method, MoCo, which achieves a correlation coefficient of 0.3521 and 0.3137. The table also highlights the performance of various baseline methods, including BIL, DIST, NORM, LL, and FV, under different pre-training algorithms and architectures. The results indicate that NC100 consistently outperforms these methods, emphasizing the importance of incorporating neighborhood consistency information in self-supervised learning. Furthermore, the standard deviations provided in the table indicate the robustness of the proposed method across different experiments. Overall, the findings suggest that North Carolina 100 is a promising approach for improving model calibration and downstream task performance in self-supervised learning. This paper explores the concept of neighborhood consistency in the context of unsupervised learning, particularly focusing on its application to the evaluation of representation learning algorithms. The authors present a novel perspective on how to measure the reliability of representations generated by different functions, which is crucial for understanding the efficacy of these algorithms in real-world applications. The proposed neighborhood consistency measure, NC100, assesses the similarity between sets of nearest neighbors obtained from different functions. This metric provides insights into the stability and reliability of the representations produced by various algorithms across different embedding functions. By comparing NC100 with baseline methods, such as SIM-CLR, DIST, NORM, LL, BIL, MoCo, and FV, the authors demonstrate that their proposed metric can effectively capture the performance of these algorithms in transfer learning tasks. Moreover, the paper delves deeper into the concept of neighborhood consistency, discussing its relationship with the uncertainty principle in supervised learning. It highlights the challenges of comparing representations constructed by different embedding functions in unsupervised learning due to the lack of a unique ground truth representation space. To address this issue, the authors introduce a transformation function, phi, that maps different representations into a comparable form. This allows for the assessment of consistency across the set of representations H equals H1 x asterisk operator x asterisk operator, using a surrogate representation consisting of relative distances to reference points. The authors also propose a sparsified version of the surrogate representation, phi realsparse, and a scale-free version of neighborhood consistency, NCK, x asterisk operator, that relies on the local nearest neighborhood. They suggest utilizing Jaccard similarity or overlap coefficient as set similarity metrics, which are dependent on the intersection size, S1 intersection S2, when employing the KNN approach to determine neighbors. Both metrics provide the same order in terms of representation reliability given a set of test points. Overall, this research presents a comprehensive analysis of neighborhood consistency in unsupervised learning, providing new insights into the reliability and stability of representations generated by various algorithms. The proposed metrics and transformations offer a promising direction for future research in evaluating and improving representation learning algorithms. Here is a combined summary of pages 29 and 30 of the research paper. Uncertainty estimation is crucial in self-supervised representation learning, as it provides information about the data and the model's confidence. While estimating uncertainty in supervised learning settings is well explored, it remains a relatively undiscovered area of research in deep representation learning. Recent works have extended deterministic frameworks to stochastic ones, allowing for the construction of uncertainty-aware self-supervised representation learning frameworks. O et al. Introduced a hedged instance embedding, HIB, that optimizes a representation network approximating the distribution over the representation vector p theta, z, x, under the soft contrastive loss and variational information bottleneck principle. They proposed an uncertainty metric called self-mismatch probability, which can be interpreted as an expectation of the distance between 2 points randomly sampled from the output distribution. Wu and Goodman introduced a distribution encoder that outputs the representation of a Gaussian distribution with a diagonal covariance matrix Saint, X, and extended the normalized temperature-scaled cross-entropy loss to a distribution-level contrastive objective. They used the norm of the covariance matrix to assess the reliability of a given input. However, stochastic representation learning has some limitations, such as requiring retraining, which may not be practical or feasible for large models. Additionally, new training schemes can impose unexpected inductive bias to algorithms that are already working well. Several studies have introduced ways to detect out-of-distribution samples by determining the novelty of the data representation from a deterministic model. These methods commonly use the relative distance information of the query data point's representation vector to other reference points. Some works are designed for supervised learning schemes that require instance-specific training labels, while others estimate uncertainty in the absence of class label information. The main limitation of these approaches is the lack of theoretical justification for the proposed metric, as it is founded upon heuristic rules. A wrong selection of the distance metric can lead to contradictory results, and using a larger K in these schemes does not necessarily ensure its effectiveness. Establishing a robust reliability measure and analyzing its theoretical validity is vital for deploying foundation models in safety-critical settings.